Good afternoon, my name is Ysbrand Wijnant. Welcome to this webinar. I'm going to tell you something about the Sonocat, an all-purpose acoustic measurement device. The content of my presentation is as follows. First, I'll give you a short introduction to the Sonocat. I'll give you some theory. We'll discuss case studies, how to use the Sonocat, and I'll do a short demo. So what's the Sonocat? Well, the Sonocat is a spherical microphone array shown here. I have it here in my hands as well. You see there's a sphere, and in that sphere we have 8 MEMS microphones. They're connected to a body, and inside the body we have a built-in data acquisition system where we store and retrieve all the data from the Sonocat, and then it's passed through a USB cable to the laptop, and you can store and save all the data there. We have in addition the Sonocat software. The Sonocat software is a Windows-based software which directly connects to the measurement device. So it's seen as a sound card. So you just plug it in, and the Sonocat is recognized by the laptop. So then, what does the Sonocat measure? Well, being an acoustic measurement device, it measures acoustic pressures, of course. But since the pressures are inside the sphere, so we have 8 locations where we know the pressure on the sphere, we can also deduct the 3D particle velocity. And since we have pressure and particle velocity, we also have 3D sound intensity and 3D impedance. Sound intensity being the product of the pressure times the particle velocity, and impedance being the ratio between the pressure and the particle velocity. In addition, we have the pressure intensity index, where the pressure intensity index is the difference between the sound pressure level and the sound intensity level, and that will give you an indication about how propagating the sound field is, or how reverberant the sound field is. All these measurements that we do are in narrowband, but you can also convert to octave bands, or 1/3 octave bands, or 1/6 or 1/12 octave bands, as you would like, and we can add the A, C, and Z weighting if we want to. But that's not all. The reason why we developed the Sonocat is because we're able to separate any sound field into an incoming sound field and a reflected sound field, and this allows us to measure sound absorption. A normal regular intensity probe would measure, as shown here in the blue arrow, would measure the active sound intensity, being the net result of, so the difference between the incident intensity and the reflected intensity. Using this local plane wave method, which I'll explain in a minute, we're able to separate this active intensity into an incident and a reflected one. So we can measure the incident and reflected sound intensity, but if you would have a surface from which sound is emitted, you can also measure the emitted sound intensity. So even if you're in the diffuse sound field, you're still able to measure how much sound is being emitted from a surface, while all the surroundings of the diffuse sound field will impose a reflective sound field back, such that the active intensity is close to 0. So that having said, we can measure in situ sound absorption in a sense that we do not depend on any global sound field or known sound field that we impose. We can also measure in situ sound transmission loss and in situ sound power as if you would be in an anechoic environment, but that will come later. And all this is based on our patented local plane wave method that we invented to come up with this separation. So all the quantities that the Sonocat can measure, you can view in the Sonocat software. So the Sonocat software is built out of 4 panels, which you access at the different stages of your measurement. So first you go to the project panel. You type in the info that you want to store connected to the measurements, like an operator or a location. And you also see all the measurements that you have done within that project. So it's kind of a administrative panel. Then when you start doing measurements, first you want to see if all works well, if you are at a location which you want to measure. So then you can use the monitoring panel. And in the monitoring panel, you can continuously measure all the acoustic quantities that you want to see, so that the Sonocat software offers you. However, it doesn't save any data. So it's a real-time measurement of all the acoustic quantities. Then you go to the measure panel if you have found a location which you do want to measure and want to save the data. So then you have full access to all the measurement settings, like the recording time or the resolution in the frequency domain, and you can save all the lossless data. So the idea then is that once you've done all the measurements that you've done, you close your laptop, go to your office, and open the analysis panel. And in the analysis panel, you have full access to all the data, all the time data. You don't have to redo any calculations. It just you can analyze all the results. You can measure absorption coefficients, but also emitted intensities, since we've stored all the time data. So what's so special about the Sonocat? Well, the Sonocat is able to measure in-situ sound absorption. And by in-situ sound absorption, I mean that you can take the Sonocat, go to the sound field in which you want to measure the absorption of any material, and it will tell you how much of the sound that's impinging on the absorber is being absorbed by the absorber. So the definition of the absorption coefficient is the active power divided by the incident power. So it tells you what's the ratio of the incident power being absorbed. So for instance, if I have 10 watts of acoustic power impinging on an absorber and I have 8 watts of power being reflected, then the net result would be 2 watts and your absorption coefficient would be 2 over 10 is 0.2. So there are methods available to measure the sound absorption coefficient. But these measurement devices, which you show here, like an impedance tube or an alpha cabin, or like this Tamura method, they all require special equipment. They all require a laboratory to make a global sound field such that we have enough information to separate the incoming from the reflected sound field. So all these current methods, they rely on a global sound field, a known global sound field, like the 2 plane waves in an impedance tube or a diffuse sound field in a reverberation chamber. They have to know the global sound field, otherwise it's impossible to separate the incoming from the reflected sound power. But my statement is always that the actual absorption of an absorber depends not only on the absorber, but it also depends on the sound field that is impinging onto the absorber. So it actually depends on the in-situ sound field. To illustrate what I mean, let's take a look at an example. And the example I have in mind is a louver door. So here it's shown in the picture. So here you can see the sound pressure level on the louver door for 2 sound sources. So here, if the source is at the left bottom corner, you see the sound pressure level shown in the middle figure. And if the source is here on the left top corner, you see the sound pressure level shown in the right figure. Clearly they're different. And that has to do with the direction of where the sound is coming from. So here, if the source is here, is on the left bottom corner, you see most of the sound rays propagating into these absorbing segments, and they're going through the louver door. However, if you put the sound source here on the top corner, the sound rays reflect onto these reflective segments and bounce back and reflect back to the sound source. Meaning that if you see this louver door as a single absorber, then the sound absorption coefficient depends on the sound field. If the angle of incidence is here about 45 degrees, then sound is going through, and if it's minus 5 degrees, sound is reflecting back. So it's the same material, but we have a different sound source. So that means a different sound field and a different absorption coefficient. So the acoustic absorption depends on the material, but it also depends on the actual acoustic environment. And this is where the Sonocat comes in, because the Sonocat can measure the incoming and reflecting sound intensity. It can thus measure the sound absorption coefficient in the actual in-situ sound field. So you don't need to use any artificial, well-known sound source, sound field. You can just use the sound that you want to absorb. So a little bit about the theory. The active power is easily measured using any intensity probe. If we measure pressure and particle velocity, or if we measure pressure at different locations and deduce the particle velocity from that, we can measure the active intensity and the active power. However, in general, the incident power is unknown. So how can we deduce the incident power from the actual sound field? We do that by approximating the sound field by two local plane waves. One plane wave incident on the absorber and one plane wave reflecting back from the absorber. And by doing these measurements and mapping this onto this model, we can deduce the amplitudes of the incoming and the amplitude of the reflecting wave, respectively A and B. So once we have the amplitude of the incoming and reflected sound wave, we can measure the associated intensity, and by integrating that intensity, we get to the sound power, and we can get to the absorption coefficient. This is called the local plane wave method. Local meaning that this amplitude can change from point to point. So we're not restricted to any global sound field. We do not need to know the global sound field. We just can approximate the sound field locally by these two plane propagating waves. So when we go back to the example I showed before, you see the sound pressure levels here when the source is at A, and here you see the sound pressure levels if the source is at B. And in addition, you see the incident intensity based on the local plane wave method. Here you see a large incident intensity and a just limited reflected intensity close to a reflective segment here. While in the other picture, where you expect much more reflection, you see a variation of the incident intensity. In blue and in red you see the reflected intensity, which is a bit larger as opposed to the situation where the source was there at A. And then the associated absorption coefficient becomes clear. So here you see the absorption coefficient when the source is at A, which is approximately 1, so it's fully absorbing. And here when the source is at B, you see more and more reflection due to these reflective segments. So mimicking the more reflective behavior of the material when the source is at B. So now when we switch a bit to some advanced insights, if for instance you would measure in front of a poorly absorbing absorber. So what you generally do is you have a scan area, you scan with the Sonocat just in front of the absorber. What we did is we evaluated how the sound absorption coefficient changed with the distance from the absorber. So apparently we're not able to scan inside the surface, so inside the absorber. We should always measure a few centimeters in front of the absorber. So we measured the absorption coefficient if we would scan at different locations or different distances from the absorber. So here you see the absorption coefficient for these different distances. So if we would measure exactly on the wall, then our method would indicate a 20% absorption coefficient. But if the distances increases, you see it can even go up to 35% of absorption. So would that mean that the absorption coefficient depended on the scanning distance from the sample? No, that's not the case. So what actually is going on here is that the method interprets any leakage of energy as absorption. And when you look closely to this energy flow close to a non-absorbing absorber, then actually what's going on is that you see a lot of intensity, a lot of energy starting to flow parallel to the non-absorber. So it's a lot of energy is being lost there. So the solution is then apparent, because then you have to scan or close the gap to capture that energy loss as well. And if you would do that, so you would include the circumferential scan area, then you get the right absorption coefficient. So for good absorbers, this is not necessary at all. But if you have really poorly absorbing absorbers, then you need to scan, including the side circumferential area, to capture that energy loss as well. And now some words about the validation of our method. We did experiments in an impedance tube, and we have impedance tube results of the manufacturer of this 50 millimeters melamine foam. You see here the results of the Sonocat in blue, and that Sonocat experiment was just, we put the melamine foam in an office onto the floor where we put the Sonocat just on top, and we started to make noise with the loudspeaker somewhere about 2 meters above the melamine foam, and we got exactly similar results as the impedance tube. So in fact, in the case that the sound field consists of only plane waves propagating onto an absorber, then our method should be exactly the same. And this is the result for the 100 millimeter melamine foam. You nicely see the increased absorption coefficient, specifically at lower frequencies. So obviously we also did a lot of case studies using the Sonocat. This is one where we measured in a high-speed train in Germany. You see the absorption coefficient close to the seat, which is quite high as the function of frequency, going to about 90% absorption. We also did measurements near the window, and actually you see that the absorption is really small, and in fact it starts to be negative, and the negative absorption coefficient in Sonocat terms is just describing emission. Just let me explain how that works. So we measure the incident intensity, but we also measure the reflected intensity. So yielding an active intensity which may be positive if the sample is an absorber. However, if the reflected intensity is larger than the incident intensity, meaning that the active intensity becomes negative, this means emission from the window, in this case, to the train. And we have actually combined these two absorption and emission coefficients, saying that if the incident intensity or power is larger than the active intensity, then we define the absorption coefficient just as the active power divided by the incident power. But if the emitted intensity or power is larger than the active intensity, then you have negative intensity, there's active intensity coming into the cabin, then we have defined this alpha to be negative. So then it's minus the active intensity divided by the emitted intensity. So this is actually the same as a radiation efficiency. Well, this positive and negative alpha, meaning an absorption coefficient or emission coefficient, is very helpful in case studies like this inside a car. So here you see measurements that we've performed at different locations in the car while driving. And here you see all these lines of these different positions or different small scans that we did in whether the position is absorbing, whether if it's positive, if it's above zero, then it's positive, then it's absorbing, and whether it's emitting noise. So here you have positions where the emission efficiency is quite large. So at these positions, you really have to do something, because This means there's a very efficient sound propagation into the cabin. And you can also show that using the Sonocat software in a different way. So you have different colors indicating the different positions. And for each of these positions, we could measure either absorption when it's hashed or emission when it's not hashed. So you see there's sound actually of the location. This is the location in brown. There's coming a lot of sound from that location. Another case study that we had was a music venue. Here you see me measuring an absorber. There was a legal issue because there were two types of absorbers being used, and it was unclear which one was used at which location. And because the reverberation time was not according to specification, there was a debate about whether all the high performance absorbers were used, yes or no. So just by using the Sonocat, holding it in front of the absorber, we could easily see the difference between the two different absorbing materials that were being used. And it was clearly distinguishable that at one point they used the high absorptive material, and on another point they used the low absorptive material. And we could actually see which one was which. The last case study I want to mention is the case study on noise barriers. Here we did not only measure absorption coefficients, but we also measured sound transmission loss. This we can do by measuring on both sides. On the incident side, we measure the incident intensity, and on the transmitted side, we measure the emitted intensity coming out of the noise barrier. And in this way, we can measure the transmission loss. And here are the results as a function of frequency, so they're spectral results. You can see the laboratory measurements of a laboratory setup with the same material. You can see the in-situ measurements according to the NEN norm, and you can see the Sonocat measurements. And indeed, you see quite similar results where you actually see the mass law saying that if you increase the frequency or increase the mass, you can actually see an increase in sound transmission loss. So based on this local plane wave assumption, we can measure the incident and reflected intensity, and that is true for any sound field or any acoustic environment. We don't rely on any assumptions about the global sound field. And based on that incident intensity, we can integrate that over the surface, and from which we can calculate the absorption coefficient of that particular surface. In the next slides, I'm going to show you some recordings of how you work with the Sonocat software. So there's an indication about the project, the monitoring, the measure, and the analysis panel that you see here on the left side of the screen. So here the project, monitoring, measure, and the analysis panel. So here you see what's actually being done in the project panel. You can type in the operator, the location, and any project comments that you would like. On the right side, you would see the measurements files if you would done any measurements. You can also import any measurements that you've done previously. So this is a snapshot from the monitoring panel. You can see when you hook up the Sonocat and you measure in front of a good absorber, you see high absorption values as it's shown now. But when I go to an emissive surface or turn the Sonocat onto a vibrating structure, you would see a lot of emission, and then it will give you negative values. And if you put it on the table and make noise, then your absorption coefficient will be roughly about 0. So this is a short capture of what happens when you do a measurement in the measure panel. You can apply some comments in the measurements, so and then have a start delay. So when it waits for the measurement actually to start, now it's 1 second. You type the record button and you wait about 1 second, and then it starts to measure for about 4.3 seconds. Then you get the absorption coefficient. And this is the situation where you have The Sonocat was resting on the table, so the absorption coefficient for the sound that was in the room is approximately 0. And the last capture I want to show you is the analysis panel. So here you see all the measurements that we have done. So I've taken 2 additional measurements, so the total amount is now 3. You can show different quantities. So here it shows the impedance or the intensity direction, the theta or phi direction, the azimuth or the polar angle. You can measure the emitted or reflected intensity. Of course, you can also have a line plot, but you can also do this in bar plot if you're more used to that. It's a 1/3 octave, but we could do more narrow band if necessary. You can measure the intensity level. This is in the x direction, and the hashed lines, the hashed bars, indicate a negative value because the levels are always positive, but the direction could change. Here you can also see the particle velocity. In this times it's the z direction, which you can show in the pressure intensity index as an example. So here we show the absorption coefficient for the 3 individual measurements that we've done. One which is on the table, which is about 0, one which is a very good absorber, and one which is a very good emitter, saying something about the emission coefficient of the room and the emitter itself. That was it from my side. Thank you very much for watching. You can contact me if you have any questions on my email address at my forsilence.com address. Thanks very much, and hope to see you soon.